Hey there. So thanks for checking this out. Thought I'd throw something together just to help with normal distributions for you. When we talk about normal distributions, we're talking about things that, well, obviously we're talking about data sets. We've got this group of data, and we kind of look at the data and think of things like with averages. And the cool thing is when we have a normal distribution and we're talking about its average, we have a very, what they call, symmetrical situation. What we mean by symmetrical is very even, very kind of not average, but just basically when we talk about symmetrical, I like to think of the word mirror. When we think of a mirror, when we have a line of symmetry, this would be kind of our line of symmetry because to the left and to the right are kind of mirror images of each other. It's not like there's more stuff to the right and less stuff to the left, or the opposite, you know, more stuff to the left and less to the right. So if we think about this in terms of a graph, we're talking about we took this sample of something. And I always start off with, let's talk about a group of students. If you're a brand new teacher and you grab students from all parts of the world, you grab students from every walk of life and you put them in one classroom, and let's say we have 100 kids, or you could take 1,000,000 kids or whatever. Your sample size, it's completely random. You could have kids from of all ethnicities, you could have kids of all academic backgrounds, kids of all you know, financial backgrounds and home lives, everything, completely random. You're probably going to end up with a normal distribution of their grades in that class, right? You're going to end up with kids that are really good. You're going to have kids that aren't that good. Kids that know the stuff, kids that don't know the stuff. Kids that work hard, kids that don't work hard. You know, hopefully the teacher, if the teacher is just solid no matter what. Take the teacher out of it as that variable. You're probably going to end up with a normal distribution. A normal distribution of data, meaning, hey, look, it's pretty normal, and we've got this average, this mean. Everything to the left is kind of similar to the right. So if we have this average, this number, it can be anything. It could be a percent, it could be dollars, it could be minutes, it can be anything you want it to be because you're just looking at some type of data. So let's look at it from a perspective of a classroom, and we're just comparing grades. Let's say that a teacher has a normal distribution of students, and upon calculation, the teacher says, hey, my class average for grades is 75%. So when they say average, they're talking about a mean. It's the same word. When we have and the teacher goes on to say, I have a normal distribution. I have a normal distribution with a standard deviation of 6%. What that means is standard deviations are how far are you from the mean. So when we say we have a standard deviation, I'm just going to use the SD, a little abbreviation there. Standard deviation of 6%, that means that as you go to the right, you increase by 6%. So in this case, we'd have 81%. And as you go to the left, away from the mean, you decrease by 6%. So in this case, you'd end up with 69%. And you continue that. As you get to another standard deviation away, you still subtract by 6% in this case. Now I'm using percents, right? So we could have, you know, different scenarios. We could have stuff that's minutes or hours. We could have an average of 3 hours. And we could see a standard deviation of 5 minutes. Who knows? Like anything could be the numbers here. It doesn't necessarily have to be a percent. And again, we can add 6 over here, which gets me to 87%. And you can even go to 3 standard deviations away, which typically is like a line, you know, sitting way over here, because there's technically just this sliver of data that's not a part of it. And you could write it out, and so another 6%, we're looking at 93%. To another 6% looks like 57, if I did the math right. I forgot to mention, by the way, we're talking in this normal distribution is 100% of your data. So when we say we have 100% of your data, that could also mean, you know, hey, look, 50% of your data is to the left, 50% of your data is to the right. That's a normal distribution of data. It's very symmetrical. And when we talk about standard deviations, it's talking about how far away are you from that mean. Okay, distance from the mean. How far away are you? So if you're one standard deviation, that's all of this data. And when we also have a normal distribution, we tend to have very few outliers. Remember, outliers are the things that don't fit. You know, if I have a student get 99% in my Algebra 2 class, that doesn't happen very often. That's a hard class. That'd be way, way over here. That would even be greater outside of the 93% for 3 standard deviations. So that's even beyond that. Now what's cool is, because this is a normal distribution, there is this what's called the empirical rule. Okay, and the empirical rule is just something that we know in general because it's normal. This is a normal situation. This is not abnormal. This is normal. And if it's a normal distribution, the empirical rule applies, which means there's this percent of data that we know it has to have. Okay? So if you are, for example, one standard deviation, if you're one standard deviation away from the mean, then you must, or the data, the percent of data should have 68% of it, or really close to that. 68% of the data should be within one standard deviation. What that means in this case is that 68% of our class, 68% of the students and their grades must be between 69% and 81%. 61% of our students have a grade somewhere in there. Continuing on, if we are 2% of the rule, 2% of the 2 standard deviations away, if we are 2 standard deviations away, because this is a normal distribution, the empirical rule tells us, look, 95% of your data is within 2 standard deviations. Always. Because it's a normal distribution. It's a rule. Something we know must occur. Now, just to be clear, what that means is 95% of your data would be between 63%. The grades of the students would be 63% to 87%. I didn't really make that 7 very good, did I? So 87% to 63% has 95% of our class within it, which means outside of that is 5% of the student population, meaning people that got worse than 63% for a grade and people that got better than 87% for a grade. So, and that's just a hypothetical situation here, but that's what we're looking at. It's also important to note that we're talking about all of this data. So when you're 2 standard deviations away, you're including these people, but you're also including these people. Some we are kind of already counted, that 68%, they're a part of this 95. So we could even think about, and figure out what percent of data is actually in this range, just in here, not including all this other stuff. So there's math we can do, and we will in just a little bit. Finally, the standard deviation likes to mention that if you are 3 standard deviations away, if you're within 3 standard deviations, you contain 99.7% of the data. So there's this minuscule part that would mean students that got worse than 57% or better than 93%. I must have a very hard class. But that's the situation. Like, that's what a normal distribution is. This empirical rule applies no matter what the data is, no matter what. So what's cool is, let's just create a different situation here. Let's say we've got another normal distribution situation. We've got a situation where the data is normally distributed, and we're talking about a bike race or a marathon. Let's go with a marathon. See, the average time that it takes a person to finish a marathon is 5 hours. 5 hours. If it's normally distributed, there may be a standard deviation of, let's say, 20 minutes. Right? A normal distribution with a standard deviation of 20 minutes. Well, we can figure out all of these percents and all these data. We can fill this thing in. If it's, looking at this next one standard deviation away, well, then we're looking at 5 hours, 20 minutes. And if you wanted, maybe you could fill this in with just minutes. Like we could turn around and we could say, instead of saying 5 hours, could I just do, 300 minutes? You could absolutely do that if you felt more comfortable. And then you could call this 320 minutes. It's kind of up to you. And then that would make the subtraction easier, right? You'd be sitting here going, okay, 2 hours, 80 minutes, or 280 minutes, excuse me. Or you could sit here and say, no, it's going to be about 4 hours and 40 minutes. You can fill it in any way you want, okay? But we could fill this in. We could say, hey, how many standard deviations are you away at this point or this point? But you can fill this in repeatedly because you know it's symmetrical. When we have these situations, just to continue, if we have 4 hours, 40 minutes, this would be 4 hours and 20 minutes. And then you also have someone who can do it in 4 hours flat. Now, this is probably a bad example, but you can come over here and say, hey, some people take a really long time. They're longer than this. They go 5 hours, 40 minutes. And then some people take, if they're 3 standard deviations, they're over at 6 hours. So that's your normal distribution just from a data perspective. That's all you'd have to do, is utilize this. Now, for the assignments are going to ask you for things like, what is the probability that someone, let's use this, let's say they gave you this information. They told you 5 hours for the mean, 20-minute standard deviation, and they ask you something like, what is the probability that a person takes less than 4 hours, 20 minutes? If it's a nice standard deviation problem, meaning you've got the mark directly on here, okay? And it asks you for that. Versus like, what if it said, what is the probability that a person takes 4 hours, 24 minutes? There's different things you can do. Or less than certain situations. Well, we're looking at this, and we can actually use the percent data stuff that we know to figure this out without any formulas. However, we are going to need formulas for the assignment, but it's important to understand how you could use this to do it first. If we remember from the empirical rule, 68% of the data is sitting right in here, right? 68% is either one standard deviation positive or one standard deviation negative, or way less than the mark of the mean. Remember, this is symmetrical, meaning the same percent is here to here as is here to here. Half the data is to the left, half the data is to the right. So half of 68% would tell us, hey, you got about 34% on each side. Let's also keep in mind, we're looking at 100% of our data. Let's also keep in mind that if we're thinking to the left of this, 50% of your data is sitting over there. Well, it's asking us for the percent that the person took less than 2 standard deviations. Less than 2 standard deviations away. Less than 4 hours, 20 minutes. They're talking about these people. Anything to the left of this. Keep in mind, again, 100% of the data. Well, what was this 2 standard deviation? Remember how we said this is 68% and these two together are 95%, right? These group of people, but also this is your 95%. That's 95% of your data is within this range. We can break that down and we can actually figure out how much is in each of these areas. If we know that we contain 95% of our data, 95% of our data is within 2 standard deviations, and we know that this area of the data is 68%, what's left over would be in here. 68% is in here, 95% is all of it. So if we subtract away the 68%, we know what's in that gray shaded area. So in this case, with a little subtraction, oops, I don't know why I wrote the 7 up there. That's for the 7 to be down here, but 27% of your data has to be within these two gray areas. Now that doesn't mean 27% each, that means 27% total. And just like this is symmetrical, this whole thing is symmetrical. So these two are half of this 27, or 13.5%. Now let's think about this logically. We know that this whole graph, this whole chart, this whole normal distribution contains 100% of our data. We know that from here left is 50%, from here right is 50%, and in this case we only care about these people because it wanted less than this amount of time, this 2 standard deviations away. We just figured out that 34% of the data is here and 13.5% of the data is right here. What's left over here? Think back. 50% is the total. If we know that we have 34 and 13.5 here, that's going to give us, if we add them together, that's going to give us 47.5%. And remember, since we only care about these people, we only care about that, and we know that from here over, we have to have 50%. If we take 50% away from it, that's going to leave us with 2.5%. And in this case, that would be the answer to the question. If it's in percent, if it wanted decimal, you might be writing something like 0.025. So it's just decimal to percent changes. On the assignments that you're going to be asked to do for liberal arts math, this is all you're going to be asked to do, except sometimes you can't get an exact number because what they give you is information that's not precise. What if they told us that it was 4 hours and 10 minutes they wanted? That's not an exact, precise situation. Now, could we estimate it? Absolutely. If we want less than this, we know the answer is now less than 2.5%. On a multiple choice test, we could sometimes use process of elimination and figure out the right answer just based on that alone. But if that's not good enough, you're going to need a couple things. No, I'm not sure if at the beginning of this video or just literally right now. It's prompting, hopefully, I'm going to try to see. It's hopefully prompting you or has prompted you to download a file. That's a Z table, and you are going to need that. We'll explain what it's used for in a little bit. But it's going to be used for when we don't have these perfect situations. When they're not asking us for a percent or a probability on a perfect mark of this standard deviation. It's asking for, in this case, like when I did that scenario of 4 hours, 10 minutes, it's asking for like the mark right here and this percent of data. So we can't quite know exactly what the answer is, but we can estimate. And that might very well be good enough. However, if we don't know what the standard deviation is, that's where the formula from the class, or this formula in general, is going to come from. And we have to know what each of these represents. I'm hoping I did this. I think I got it backwards. This actually goes in the denominator. I believe this little U shape goes right up here. Pretty sure that's right, but let me double check. Yep, so this formula is accurate, but knowing what it is, that table that I gave you, that PDF file, that's going to be this value. It's not going to be your answer, but it is going to be the value. And we could actually, eventually what we'll do is we'll use this one for an example, just to test it out. So we'll come back to that in just a second, but I want to break down what this is. This formula will get you what's called a z-score, a raw score, a standard deviation number, so to speak. And we can use that number and that table to get probability questions or answers to that. And this is the part that will show up on the test, or assignment, I should say, for liberal arts math. So important that you follow along with this, because you can estimate using what we talked about earlier, but this is to get a close to precise answer. And understanding this, the first thing is the x is just your variable. It's what you changed. Going back a little bit, if we go back and remember when I told you, what if they asked us for a time that was 4 hours, 10 minutes? That's our variable. That's the thing that could change, because I could easily go and say, hey, how about 5 hours, 5 minutes? You know, that's where you have to get the number that changes depending on the situation. This little symbol right here actually just represents your mean. So what is your average? And what do they tell you? If we go back to this situation, 5 hours or maybe 300 minutes. That was our average. That was our mean. And this last little symbol is our standard deviation. So remember on the problem before, I probably should have typed this out. Sorry about my penmanship. Standard deviation, that looks horrible. Well, I paused the video to write that word, but it didn't come out too much better, but I think we can survive. Anyway, remember, this is that value. The standard deviation is how far away are you from the mean? Every time. How much more did you get away? How much further did you get away? And that could be a very big number. That could be a very small number. Standard deviation is just, because it's a normal distribution, it's showing us how far away from the mean are we getting after every standard deviation, after every value. So again, these can be anything almost, depending on the scenario. It can be percents, it can be minutes, it can be hours, it can be days, it can be feet, it can be anything really that is kind of measurable. So if we can do this, we can get a z-score, a raw score, and using that, we'll use the table that you have, which I'll show you at the end, to get an answer. But the scenario we're going to use is going to be from that other page. So in that scenario, I talked about running a marathon, and I said, hey, we've got a 5-hour marathon average. And instead of hours, just to make things easier, I am going to use minutes. So if we're looking at 5 hours and there's 60 minutes in every hour, we're looking at 300 minutes. And I said that the standard deviation value was 20 minutes. So this would be 320 for one standard deviation away to the right. This would be 340. And over at really far over here, you might or would have 360 minutes. And when we go to the left, we're going to subtract 20. So that would give us 280, 260, and again, somewhere way over here, that little mark just to show the end for 240 minutes, which, all right, so we've got this scenario laid out, and we can visualize it, and we should fill it in. It's always a good habit to do that. But what if the question turned to us and said, what is the probability that a person takes less than 4 hours and 10 minutes? Well, in this situation, because I've transferred it to minutes, we probably would want to start off just by saying, hey, how many minutes is that? So if we have, 60 minutes times the 4 hours, we're going to end up with 240 minutes. So 250 minutes is what we're looking at. Well, in order to use that information above, we're asking for that probability. Now remember, we talked about it. We already found that this is about 2.5% is sitting in there, right? But we're less than that. So our answer should be less than that percentage because we're even further to the left. We're even less of the data is contained within this very approximate 250 mark. We can use this to figure out the actual answer. X is what's the variable? What changed? Well, they're telling us in this situation 250 minutes is what we want. So that would be our X value. Remember from the formula, the U symbol, I like to call it a U, I think it's a U, but it's just our mean value. And in this case, that would be 300 because our average was 300 minutes. And it's over or divided by our standard deviation. So that standard deviation value was every 20 minutes. And remember, this isn't giving us an answer. It's going to give us a value we can then use to get an answer. So we plug in this total. Obviously, you're sitting up top going negative 50 over 20. I believe that's going to come out to negative 2.5. Always dangerous doing that live. So negative, oh yep, negative 2.5. That's our z-score. That's our raw score. So that's what we would do to get this value. And remember, we're trying to get a precise answer. This value then gets thrown in, or we use the z-table. Now remember, the number is negative 2.5. And this is where we're going to do a little app share. So let me get that set up here. Cool. So hopefully it will show up on your screen, or if you want, you can pull up your standard deviation table, that thing that I took to you. We'll look at these values to the left and to the right. Very, very important that we have those. Notice that the number was negative 2.5, right? Well, we've got this value going on here, and if we look, we've got these numbers here. Notice how this number is kind of in addition to these numbers. Like if I wanted 1.01, I would go to 1.0, and I'd come over here, and I get my 0.1. All right. If I was looking for 1.43 or negative something, I would come up here. Let's say I'm looking for negative 3.68. Well, then I'd go and I'd find negative 3.6, and then I'd go over and I'd find the 0.08, because that's that hundredth spot, negative 3.68. These are all of your probabilities. These are also, we could convert them to percents. But remember the number we were looking for? It was negative 2.5 in this case, and I know that I showed you that 2.5%. They're not connected. It doesn't work that way. It just ended up getting a little lucky. But if we come to negative 2.5, and if it was exactly negative 2.5, which in this case it was, then that means the next number is 0. Well, there's a 0 spot for the hundreds. So negative 2.50 is this number. Okay? It's this number. 0.00621. Let me kind of pause this real quick. Let's kill the app share and come back to here. We got a value that was 0.00621. What that means in this case is that about 0.6%, less than 1% of our data would be to the left of that z-score. That's what they were asking for. Who can run faster than that? So that's how we use this formula to then find out an exact percent of data. Also, what's cool, just to show, what if it said, what is the probability, I said and a person, that a person takes longer than 4 hours and 10 minutes. The cool thing is, we don't have to do this formula again. We would do everything the same. But I want to point out something that it says on your table really quick. If you look, notice how it says the area to the left of the z-score. What they're talking about, right? And it says it on the second page too, if you look. Area to the left. What they're talking about is, if you're looking at this, it's talking about to the left of here, the percent of data left of here, or probability of data, which we can then take the probability and convert it to a percent. To the left. Well, if it asks for longer than 4 hours and 10 minutes, do I want to the left? No, I want to the right. And if I want to the right, and I know that it's out of 100%, then that means there's a whatever's left over, which is a lot, right? This was 0.6 from this area over here that we just calculated. Well, then to the right is everything that's not in that 0.6. Everything out of 100 that's not 0.6%. So we're looking at this answer to this question would be 99.4%. 99.4% of people take longer than 4 hours and 10 minutes to run a marathon. Now, by the way, this is just completely random data, probably not at all accurate, but that's what we're working with here. That's what we're trying to do. I'm going to record one more problem to kind of work through, and then hopefully that helps and you can try it on your own. This is one from the lesson. We're going to use it here. We're going to do a little estimation, then we'll get the precise answer just like we did in the last one. So we've got this scenario, and I know it's probably confusing when it says take another look at something that the lesson never mentioned before, and that's because they grabbed this from another class, and I just want to make sure that you guys are aware of that. But we can still use it to answer the question because it gives us enough information. So we've got these two pizza places, all right? And if you want, take a minute to kind of read this question. Get that mean delivery time. I'll just kind of read through it here. We've got this DeLucas pizza takes a mean of 32 minutes and a standard deviation of 5 minutes. So every one of these would be 5 minutes, difference from the mean and from each other. And they want to be sure that this person that's ordering, like let's say it's you or me, we want to order a pizza, and we've got these scenarios, right? And we're trying to pick which pizza place we should order from because you know what? If we don't get our pizza in 30 minutes, we got problems, all right? So we've got this data, and we can analyze this data to figure out which pizza joint we should order from because we want the most likely we can find. Well, let's run through this scenario first off. Let's just focus on DeLucas because we'll end up doing this twice. DeLucas says, hey, our average time is 32 minutes. Well, already I'm concerned, right? I'm like, wait a minute. Your average is 32? The reason I'm concerned is because half the data is to the left, half the data is to the right, which means I've got a 50% chance, because it's 50-50, of getting it in 32 minutes. I've got a less than that, because I want the standard deviation, I want 30 minutes. And this thing has a standard deviation of 5 minutes. So if I want, I can fill this in and go 5 minutes less than this is going to be 27. Is it standard deviation? No, standard deviation of 6 minutes and 5 minutes. So each one has different standard deviations. So for DeLucas, it's 5 minutes away, which means we're going to end up with 27 minutes, 22 minutes, and again, 5, we're looking at 17 minutes. We also could, just to fill it in and feel more comfortable with this, if there's one standard deviation away, we're looking at 37 minutes. Another one, we're talking about 42. I guess the delivery driver got a flat tire. And way over here, 5 more minutes, 47 minutes. The pizza guy deserves to be fired. I'm just kind of joking around, but this is the kind of real-life application. You can kind of play around and have fun with these. You can start talking about what might have happened. So in this scenario, we're looking at this, and we know if we're looking at 32, the 30-minute mark somewhere like right there. And again, I'm just estimating, but that's about where it is. So we know just visually based on this and go, well, it's going to be less than 50 minutes. And remember the empirical rule stuff? Like we can break down what's inside here and what's inside here. We know that this is 34%, because remember it was 68 divided by 2. This was 13.5% because we did the 95% divided by 2. So we can estimate, but we can even just visualize and go, hey, it's less than 50. If this is 13.5 and this is, this gets really close to 3, just so you know. But, you're only looking at right here about 16, 17% of the data. So that's a wide gap here. And that makes sense because most of our data should be here because this is a normal distribution. Remember, everything we've talked about is about normal distributions. Lucky for you, this isn't statistics class because not everything's normally distributed. But all we're focused on is this, normal distributions. This is one of those situations that because it's not perfectly on a standard deviation, to find out the precise value, we have to use this z-score. We know it's less than 50%. We know it's less than 50%. We know it's going to be greater than about 17%. Right? So it's somewhere in there, and that's a pretty wide gap. That's why we're going to need this. We could estimate just looking at it visually and go, I don't know, 40%, 45, but who knows? So we need this. Remember, X is our variable. X is the thing that changes. How many minutes was it? The other thing is our mean, right? It's our mean. It's our average. And the bottom one, that little symbol, that's our standard deviation. I'm going to use SD. We get the z-score using this formula. We then use that z-score and the z-table to get our answer. We do have to think about left versus right. So keep that in mind. Left versus right. So if we come into this problem, we said, well, it's going to take them about 32 minutes as the average. I need it in 30 minutes. That's our variable. That's the thing that can change. Our mean is always 32 minutes for DeLuca's, and his standard deviation, though, is about 5 minutes. We come to this and we say, okay, so we're looking at this. We got 30 minus 32. We've got a negative 2 over 5. We've got negative 2/5, which we would then get as about negative 0.4. Negative 0.4. You might even throw in that 0. So we've got that value, negative 0.4. That's where we would go to our z-table again. You can pull it up and look for yourself. I'm going to app share it here. We go to that table. Remember, we're looking for negative 0.4. Remember, this side is your numbers, but look, they also include the whole numbers of being 0. So there's my negative 0.4. And remember, I didn't have a number after it. So it's negative 0.40, which is this number right here, 0.34458. 0.34458. So if we stop the sharing, it came out to 0.34458. And I do want to remind you that that is to the left. And remember, we wanted less than 30 minutes. So we're looking at a situation where if we move this over and make it a percent, we're looking at about 34.5% chance that we're going to get this pizza in time. DeLuca's, it's not looking good, but here's our scenario. Our scenario is such that you would want to compare the other person and see which is best. Okay? Even though this is saying, hey, don't really need that. So we know that they're not good. We're unlikely to get our pizza on time, but we got to choose between one of these two. So we're going to sit here and we're going to do the exact same thing one more time using the information we had. So I'm just going to keep this other one. If we go to the probability again, if we go to the information again, it says, hey, we still want our pizza in 30 minutes, but this other pizzeria, this Vinny's, well, their average is 31 minutes. That sounds good. Right away, I'd be like, well, they're closer to it. Let's use it. But when they got problems, they got problems. See, 6 minutes, their standard deviation is a bigger gap. That's a problem. They look like they don't have as tight of a standard deviation, meaning there's more variance, there's more change involved. And that can affect probability as well. So we come over and we know that changes to a 6, which gives us negative 1 over 6. And to get that decimal, you might use a calculator if you're not sure. You do 1 divided by 6, or negative 1 divided by 6. That's going to give us about negative 0.16, and it goes on forever and ever and ever. So you might grab, since technically, remember we need these two numbers. We don't have the whole number here. So I'm going to use negative 0.17, since that technically would round up. All right? So we would one more time go to our probability, and we're looking for negative 0.17. Remember, if we don't have a number at the front, that's our 0. We're looking for negative 0.1, but now we need this line of work, and we're going to need, I'm going to kind of maximize this and maybe shrink it down so we can see this thing a little bit better. Cool, there we go. Negative 0.1, and I need 7. So I'm coming over here, and I'm going to use this number because there's my 7 spot for the 100th spot, and that's giving me 0.43251. Now we're going to write it down, 0.43251. I'm going to use 0.433. 0.433, I'm going to round it a bit. But that means this other one, 0.433 is the probability, which means the chance is 43.3%, which means we're going to choose Vinny's. Because even though it's not likely that we're going to get our pizza within 30 minutes, 43%, about 43% of the data would be 30 minutes or less from Vinny's. 34.5% of the data would be less at DeLuca's, less time than 30 minutes. We can also flip this. We could use this data. Remember, this is always to the left. So the only trick question they sometimes will give is they might ask you the opposite way. They might ask you for this data, the stuff that's not here, right? That's not at this 30-minute mark. What if it's greater than? Well, you just take it out of 100. Since this is 34.5% of the data, that means 65.5% chance it's going to take longer than 30 minutes. This one, 56.7, if I'm doing the math really quick, 56.7% chance it's going to take longer than 30 minutes at Vinny's. All right, so that's how we use the formula. That's normal distribution. I really hope it helps. Give that assignment a shot.